This is GKE hypercluster, powering secure planetary scale for AI workloads. Today I'm joined, not on stage, but I'm joined by two other people. My name's Glen Messenger. I'm a product manager at Google. We've also got Greg Castle, who's a principal security engineer for GKE. He is our technical lead for all things Kubernetes security. And we're joined by Nova DasSarma as well, who's the infrastructure lead from Anthropic. And today we're going to be walking you through GKE hypercluster, which is a new initiative that we launched just today, actually. We've tried to keep the agenda fairly light. We're probably going to have a packed 45 minutes, but if we do finish a little bit early, please come and ask us questions. If we run out of time, grab us in the hallway or come up the front. Plus, Greg and I have a discussion group tomorrow, so if you have really hard questions, come and ask us then, or probably default to Greg for the really hard ones. We're going to go through a very brief overview on what hypercluster is. We're probably going to spend 2 or 3 minutes talking about that. Then Nova's going to come up and talk from Anthropic's perspective about frontier AI infrastructure. And then Greg's going to do a very deep dive into model query and response protection and a lot of the security implementations that we put into hypercluster. And then finally, if we've got some time, I'm going to talk about the scale aspects of hypercluster, which are very important to what we're trying to do. To that end, let's jump in. So we partnered with Anthropic to solve 2 primary problems when it comes to hyperscale: security and scale themselves. And these are really hard problems to solve by themselves. They're incredibly hard to solve together because it's usually architecture pulling in different directions. When you think about hundreds of thousands of nodes or millions of chips, security isn't just a configuration. You really have to change the architecture itself, change the way the workloads are deployed and isolated, and who has access to those workloads. How do you verify that access, and what can those workloads do afterwards? In addition, for scale, if anyone here has worked with Kubernetes, you can't just keep throwing nodes at Kubernetes clusters. It does not scale infinitely. So what do you do when you have hundreds of thousands of nodes across different geographical locations? So GKE hypercluster was purpose-built to solve these 2 problems initially, and we've done it in partnership with Anthropic. Today we're going to be talking a lot about the modes of hypercluster. And this is important, and I kind of want to overemphasize this because typically you couldn't do security and scale together. We have a default mode of hypercluster, which out of the box, you get global orchestration, which means that you can spin up nodes and workloads globally across all GCP regions in a single cluster. And I'll talk about that a little bit more when we talk about scale. We also have sealed mode, which is exactly the same as default, but you have an additional layer of zero trust security implemented on top. So we do attestation from the firmware to the pod spec. We do isolation from platform admins and SREs, and we do a few other things that Greg's really going to drill down into. But the point I want to make sure comes across here is it's not a choice between the 2. You can have both on the same infrastructure, the same control plane, and the same experience. Having said that, I'm going to hand over to Nova.
Thanks so much. Just going to give you guys a brief overview of sort of like the kinds of things that we do. So hi, Nova, infra lead at Anthropic. We build Claude. You may have heard of it. We build planetary scale infrastructure, so we are building things around the world in most geographies at this point, and we do both training and inference across like all of these geographies. It would be a lot easier if we didn't, but we don't do these things because they are easy, but because we thought that they would be easy when we started out, and we kept going. We want to build for a race to the top on security. We think that both your data as well as like the models themselves are both going to be extremely important and transformative, and also something that need to be protected in a whole bunch of ways. And we encourage everybody to do some of the things that we're doing here on security. We're really excited to partner with GKE on hypercluster for that reason, and to provide like protection for these weights under our RSP. We're building towards architectures that are zero trust, even towards the infrastructure operators themselves. In a lot of cases, you care about your data being private, even as you're doing inference with a foundation model. And there's a lot of ways that you can imagine doing that, including trying to build things in your data center, trying to do segregated personnel and things like that. In practice, because of the way that these clusters are built and because of the investment required, it's pretty important for frontier models to be run by infrastructure teams that might be too big for your company. They might be too big for our company. We hope not. And it's important to be able to protect things along the way. In hypercluster, we want to be able to marry the orchestration workflows inside of Kubernetes with the power of something like a sealed VM that allows us to attest that the workload that is running has all of the security properties that we expect, and give people a reason to trust, or trust but verify the way that we're building this infrastructure. So your workload is booting inside of a sealed enclave. Well, in this case, it's going to be a container that's booting on a runner, and there's evidence that's presented to the storage itself to get the models in the first place. And only then after the challenge is completed, is the model itself released. And so if something is like unattested or tampered with, there's a measurement mismatch, and everything sort of fails to start in the first place. We've done a lot of co-design with Google on this. This has been I think a year-long process, maybe longer at this point, since Google came to us and was like, hey, how can we solve this problem? We want to have an orchestration service that is built for many, many node, but dense clusters. So TPUs bring a unique challenge in accelerators in general because of the powerful sort of ICI scale-up network, which allows you to coordinate multiple nodes inside of the same workload, which is awesome, except for the fact that that means that when you think about Kubernetes, this means that your workload is running across a large number of nodes, but it's like not very dense. And in practice, what that means is you end up with lots of nodes, lots of node problems inside of that same management plane. And so hypercluster helps us with runners to be able to densify some of that, and I think that makes it easier when you're sending a few hundred megabytes of data back to your kubectl every time you do something instead of gigabytes. That isn't always the ratio, but we do our best. And the GKE team has done an incredible job of allowing us to run our service on their service. So we've built things together like custom networking to be able to make sure that the way that these runners fit together works with the way that we do addressing IPv6 and non-sealed mode on these as well. I think has been extremely important because you can't just move from one mode to the other and all at once. This is a node pool level change, which allows us to incrementally migrate workloads, which has been really important for adoption. And we also want to be able to support training like this, which I think is pretty exciting for us. And we're now in production for some models. Well, if you're interested in this, please reach out to your AE. We want to do more stuff like this. We talk about scale a little bit. There's this 64-to-1 ratio here. This is primarily on the node side, and it provides relief from heartbeat traffic, total number of daemon set pods in very large clusters. It's not the only dimension of scaling, and we've worked on a whole bunch of things here, but it's been pretty exciting for us. Yeah, it's used for inference on current generation of TPUs. And so where's this going for us? We want to solve other kinds of scaling problems here. If you think about the pod architecture, like I said, we didn't actually solve that one exactly here. So there's a concept around you might want to have something like a replicated pod to reduce the total pod spec. That might be something that you can think about. We also want to build stronger boundaries on these primitives. So today we have some things in confidential and some things that are not. There are different features that we might need to have to actually get everything over into confidential mode, which allows us to have better fungibility without reduction in capacity. And we also want to try and do this with other accelerators, which is available, but we haven't adopted it yet. I'll pass it back to talk about AI asset protection.
Thanks, Nova. So let's talk about this thing that we built. So we mentioned there were two use cases. We're going to talk about the security one here, this AI asset protection. And we're going to break it down into these four parts. So what is the GKE hypercluster sealed? Who's it for? How it does the security jobs that it's supposed to do? And then how it works under the hood. So if we think at the sort of the very highest level, what we're trying to do here, we're trying to protect these AI assets. And we do that by encrypting them and then only ever decrypting them when we can prove that the code that is supposed to be decrypting them is actually the code that's running. And so we have these attestations that allow us to create those proofs, and that unlocks these encryption keys that protects the model and protects the query and response. And as Nova said, this is serving some Claude right now. It's ready for production, and we've really designed it to work at really large scale. Who's it for? So I'm pretty biased, but I think GCP and GKE is the best security of any managed Kubernetes product on the market. And I think if you ask any independent contractor who works across multiple clouds, they will actually tell you the same thing. But the point I'm making here is that there's already a lot of security you can do with GKE and GCP. We've got a big word cloud list of things you could add into your cluster and GCP security features. So there's already a lot you can do to deprivilege admins, to inspect and control any access that the cloud provider might have during support operations and that kind of thing. But here we're really dialing that security up to 11. So it's like we want to remove all the human access. And in the process of doing that, we're actually willing to accept some operational friction. So when you remove all of that access, you can't do things like kubectl exec anymore. You can't SSH into the nodes. And so troubleshooting and debugging does get harder. So in addition to those security goals of why you might want to use this, the other reason you might want to use this is if you need to prove something to an external party. So prove exactly what code is running and prove that to an auditor or a regulator or something like that. Let's talk about the security of it. If we look at a really basic model protection diagram today, essentially what happens is you would have your CI/CD system that's producing your model. It would encrypt the model and publish the encrypted model into some sort of storage, so like cloud storage. And then on the right, you would have your inference server download that encrypted model and then decrypt it using the KMS key. Really basic, kind of high-level model protection. So why would you use sealed VMs? What problem are you actually solving here? If we can already do that kind of thing, why would you need to go further? So here's a hypothetical where the inference server accidentally leaks a token, a privileged token, into the logs. And this might be, maybe you made some sort of API call, and you wanted to log a detailed error message, and you accidentally put in the token when you were writing that log message. And so you can imagine an admin that doesn't actually have direct access to the system. It's been well protected with those other controls that I was mentioning. They can use that token to download the model and then decrypt it using the access through KMS. So that's kind of the gap that we have with the standard protection, and then we'll look at how we solve that gap with the sealed VMs. So with sealed VMs, we make a couple of green arrows here, and so those green arrows are protected by attestations. So the code that's running in the sealed VM, that pod, those containers, is being measured in a really complete way and is providing proof to the IAM system that checks that this is exactly the code that's allowed to download the model. This is exactly the code that's allowed to decrypt the model using the key. And so that's how we provide that protection. So if we put the attacker back in the picture again, they're in the same position there. They still have that token, but they can't produce those attestations. And so the access would be denied at both of those places, downloading from GCS or decrypting with KMS. So that's model protection. Let's talk about query and response a little bit as well, too. So a modern inference system isn't quite as simple as just query goes in, model comes up with an answer and spits out answer. There's a lot of pieces in a real production inference system. And we've laid out a few of them here that you might have. So you might have a inference API router that's deciding where this request should go. You might have some responsible AI filtering that's doing some checking and possibly modifying the prompt or the response. If this is a video or image model, you might have multimodal processing that's operating on those inputs. And then eventually the query is kind of like makes its way to the model server, and then the response makes its way back through like a similar set of boxes. And so if we take a really basic sort of protection system here, we would encrypt the query on the left-hand side, and then have each step, we would have it decrypt the query and operate on the plaintext query, maybe change it, re-encrypt it, and then send it on to the next piece in the puzzle. So that's what a sort of basic query and response protection might look like today. So where's the gap in that system? So, and what does like sealed VM solve for us? So imagine now we've got a malicious admin, and they have control of the pod spec. And this might actually be like pretty well protected. You might have to check in code. You might have to get 2 parties to review that code before you can actually change the pod spec that is delivered into production. But like, say all that's possible, and they can change the pod spec in a way that changes the behavior of the pod, and it allows them to leak out any queries or responses that the system's seeing. So that's the sort of attack that might be possible here. So if we add in sealed VMs, then we get these green arrows again. So now we've wrapped each of those pods that are operating on the plaintext query or the plaintext response inside a sealed VM, and each one is producing an attestation to be able to decrypt that query or decrypt the response. And so not only can you do it at that layer, but you can also have the sealed VMs authenticate each other using these attestations. So if you're the responsible AI filter, you know that you will only ever be called by the inference API router, and so I should always see an attestation from the official inference API router when I'm being called by that process. And so these horizontal green lines here can be added at the application layer once you have these attestations as well. And so if we put our attacker back in that picture again, we have this malicious pod spec. When that gets scheduled on the sealed VM, it doesn't match the policy for the pod specs that are allowed to run on that. So remember, we're measuring everything inside this VM, everything inside the pod, and if all that doesn't match, then it won't run. But even if it did run, it would get measured, and then and produce an attestation, but that attestation would be different from what's being authorized in KMS. And so even if that pod spec could run, the attestation would be different and it would fail authorization, both at KMS and then also on those service-to-service calls as well. Okay, so that's how we solve security and like how it helps. Let's talk about how it works. This is a regular GKE node. So if we look at a regular GKE node, it has quite a few admin interfaces. So you can kubectl exec to the kubelet. You can SSH into the node. You can use VM Manager to change things about the VM inside the VM. And the whole node is shared by these system daemons, which are things like logging, monitoring, networking daemons, with all of the customer workloads as well, too. So we have sort of like a local control plane that's the kubelet, and mixed in with the data plane that is the actual workloads doing the work. And inside of GKE nodes, we have shielded nodes that already do quite a lot of measurement of firmware, bootloader, and kernel. It doesn't go as far as the workload, though. So we measure some basic stuff and then require that all of that is official builds to be able for the VM to even boot. But we go further with sealed VMs. So if we look at sealed VMs, and we're going to take TPU first, and then we'll do GPU next. You can also use them with CPU as well, too, but we've been focused mostly on the accelerator use cases. So what we've done is bring out all of the Kubernetes bits and stick them on the left-hand side here. So all of those admin interfaces are out on the GKE node. We call it the control node. And then on the right-hand side, we have this sealed VM. And there's no kubelet there. It's not a node because there's no kubelet. And we've got just enough inside of that VM to be able to run a container, run a pod, sorry, multiple containers. So we've really crunched down what's called that trusted compute base, the amount of stuff that's inside the trusted box to be as small as possible. And all of that is running inside of this Titanium Intelligence Enclave, which is actually part of Gemini Private AI Compute. There's a link at the end about a bunch of information that Gemini has published about how that system works. And so we're reusing some of that infrastructure here. So we have this enclave, and inside of that enclave is the TPUs, the VM, and what we're doing is measuring everything inside that TIE enclave, everything that's needed to run the VM, and then measuring everything that's inside the sealed VM. And so the combination of those two measurements means we can go all the way from firmware on the hardware all the way up to the pod spec with these measurements. And if you want more details here, definitely come to the breakout, and happy to talk about this in more detail. If we look at GPU as well, then essentially it's the same security idea. Same security idea. but using NVIDIA's implementation of confidential GPUs. So we still have this protected area that is the sealed VM, and really the difference there is the GPUs aren't directly inside the enclave. They're out on the side here, and they communicate over an untrusted PCIe bus and use a bounce buffer to move memory in and out. So you have to encrypt memory to move it into the GPU and move it out of the GPU. But otherwise, it's delivering basically a really similar sort of security system. OK, so we talked about GKE hypercluster. What it does, it provides this sealed environment that's really well suited for protecting these critical AI assets. It's for people who really want to dial security up to 11 or have like really high transparency requirements. It protects assets by encrypting them and then only allowing decryption inside of those sealed environments. And the real sort of innovation here is that we've separated out the Kubernetes stuff from the workload stuff. And it turns out that is super useful for scale. And so I'm going to pass it over to Glen, who's going to talk some more about how that actually helps with scale.
Hi, everybody. Thanks, Greg. That was really good. I want to briefly talk about scale. I only thought I was going to have 5 minutes to talk about scale, but Greg's given me more time than that, so I'm going to talk a little bit slower and welcome some questions at the end. I want to remind you that we built this not just for security, but for scale as well. And I really want to focus on the hero job when it comes to having to do things beyond what typical Kubernetes can do. It's not a criticism of Kubernetes. I work on the Kubernetes team. It's simply talking about how we've extended it beyond what it can currently do. So the training job of yesterday, and I'm emphasizing a few things here, you could succeed on that with about 10,000 chips. You could do it on a single cluster in a single geographical location or a region, and you could do it within the confines of a typical Kubernetes architecture. That was built for purpose. It could definitely do that. Today, the needs are a little bit different. We've got a certain type of customer, frontier AI customers, who don't need tens of thousands of chips. They need hundreds of thousands of chips. And they need hundreds of thousands of nodes. And most typically, this goes across geographical locations as well. We built GKE hypercluster to solve security, but also to solve scale. And I'm going to run you through some of what that means for us. Because we heard from a lot of customers, when they got up to this scale, they had to deploy lots of Kubernetes clusters. They had to deploy Kubernetes clusters in different regions, different cloud providers, different chipsets. So they all ended up with this operational sprawl. We have some customers who have tens of thousands of clusters, not just for training, but they have this operational sprawl. Then the infrastructure gets in the way of progress. What we try to do with hypercluster is radically simplify that through some architectural changes and some key decisions that we've made along the way. So Greg mentioned just towards the end about what the typical GKE node looks like, and he was spot on, but it's not just for security, it's for scale as well. The typical GKE node has your workloads on it, and you might have one or many, depending if you're doing bin packing and you care about node density. But you also run our workloads, and Greg used the example of logging and monitoring or networking. You also have the kubelet, which is huge in some cases, SSHD, OS agent, but that node is running quite a lot. And that's really bad from a trusted computing-based perspective. It's also not great from a performance perspective. You've got a lot of noise happening on that node. For hypercluster, we strip that out. We put on the bare minimum to run GKE on that node. So we have an agent that talks back to what we call the control host, which we'll go through in a second. And we have containerd. And we also focused on good put, not bin packing, which we'll talk a little bit about later as well. So I don't want to compare hypercluster to Kubernetes. That's not really fair, but that's exactly what I'm going to do very quickly. So Kubernetes, it's difficult when you have lots of nodes talking to the control plane. If you have 65,000 nodes, and by the way, we've had people that have scaled this up to 130,000 on GKE. We announced it at KubeCon last year, I think. A typical Kubernetes cluster, if you have 65,000 nodes, that control plane is struggling. It is holding on for dear life. If you have 250,000 nodes, it does. It simply cannot handle that scale, and that's fine. That's not what it was designed to do. It was not designed for planetary scale. When you look at hypercluster, we introduced this control nodes, which offsets a lot of the elements that would run on that node. And we've done some testing. We can have up to 128 runner nodes for every control node. And we can have 2,000 control nodes for a single control plane. And if you do the math, there's 256,000 nodes. And if you're using TPU v7x Ironwoods, that's a little over 1 million chips. So if we take a step back, and I really want to emphasize a few things here. If you deploy a hypercluster, you've first got the control plane, and this is not a hypercluster control plane. This is the standard GKE control plane, right? Hypercluster is a data plane implementation, but the control plane is the same one that we do everywhere for our regional clusters, for example. We've got our backend on Spanner, which we call K-span. We've spent years investing in our control plane to handle scale, performance, price performance, security. So it runs on this typical control plane, and this means you can run hypercluster and non-hypercluster node pools side by side. Underneath that, we've got the control nodes. Again, we can handle 2,000 of those control nodes, and we're continuing to push that level. And you can have 128 runners per control node. And the key thing about these runners is we really focus on them not being in a single geographical location. Because the ask from customers when they get to this scale, they typically go cross-location. They typically acquire accelerators, whether it's GPUs or TPUs, in multiple GCP regions. And we don't want to constrain them to a single GCP region. So when we designed this, we designed it for the fact that you could spin up a cluster in US Central 1, for example. You could spin up nodes, well, runners, let's call them, in US Central 1, US West 1, Australia Southeast 1, for example. And you can connect these as a single resource pool. So now you can have all your capacity, up to 256,000 runners, across all of GCP, pulled together as a single resource. You can schedule your workloads on it, single cluster. So geography stops being a constraint of what you can do on GKE. Now, to do this, we had to make some architectural decisions, and Greg went through quite a few with the security side, which was fantastic. I want to talk about some of the non-security ones. The first one is single tenant. So one workload owns the entire host, in some cases the entire rack, because we are very much focused on accelerators and TPUs, which we'll go through in a second. Second one is performance. We wanted to have the minimal footprint, not just for the trusted computing base, but also just for resource utilization on the nodes. The third one is workload to slice. So the scheduler doesn't just place pods. It packs workloads into topology domains. So we have an additional layer of intelligence there when we're doing the scheduling. And the fourth, we focused on good put over bin packing. So we really want to focus on maximizing accelerator utilization rather than node density. And this is very different from the typical type of placement that we see on GKE. If you want node density, this probably isn't for you. But if you really want to focus on good put, and eventually we're going to get good puts, without saying too much, up to like 300,000 chips, it's going to be the high 90%. That's what we're really focused on. How do we future-proof ourselves to get to that level of good put and MTTR as well? So these 4 decisions, along with many other ones, is how hypercluster can do the scaling that it needs to do. We are very early in this. It literally only launched today. The documentation online went out 15 minutes before we stepped on stage. So the roadmap is very focused on just a few accelerators. And because we're partnered with Anthropic, we focused on V5Es, V6Es, and V7X TPUs. We also support GPU H100s and some CPU families. And when I say support, they work across the default mode and the sealed mode, because we don't want to introduce support for one thing in one mode that we can't do in the other. So we want to make sure that attestation and everything else works there as well. I thought we'd be at 46 minutes now, but we're actually cruising. We've got 17 minutes left. So I want to do a wrap up. I want to do a quick recap, and then maybe we can do some questions. We got challenged by Anthropic for a really hard problem. We operate at scale. Anthropic really operates at scale. And we appreciated the partnership. And the first challenges that we had, I think it was July last year, Nova, give me huge scale and give me huge security at the same time, and don't compromise on either. That's not a small ask. So we built these 2 things into one platform. We built the security that Greg went through, so hardware-attested from the firmware all the way up to the pod spec. We isolated away from platform admins, your admins, isolated away from us, and we give you that verification of trust that we needed. And we also built in scale. The node runner architecture allows us to extend this beyond what we would typically do. It'll be interesting to see what scale and security we come up with next. These 2 things, which are generally hard to deliver together, thanks to Anthropic and Google, we've been able to. If you want more, like I mentioned, we've got this discussion group tomorrow. Come and ask us questions. I wasn't kidding when I said we'll ask Greg the hard questions. Greg is a Kubernetes security ninja. So please come forward at 9:45. We've also got some links. So the bottom one is that documentation that came out 15 minutes before, and I haven't read it, so hopefully it's correct. We've also got Anthropic's responsible scaling document there as well. And we've got our private AI compute, which goes through our titanium enclaves and a few other things in there as well. Having said that, I really want to thank Greg. I really want to thank Nova. It's been a fantastic partnership, and I'm looking forward to what comes next. And thank you all for coming as well.